I am bringing the instruction from this. So already it is fetched, and then I have read the value of R3 and R4. And by the time you take a call whether the branch is to be taken or not taken, already the value of R3 and R5 are ANDed. The result is available at the output of the ALU. In the meantime, this OR instruction is fetched, as well as this add instruction is also fetched. The OR instruction is fetched and decoded, and add instruction is fetched. Everything will go fine when the branch is not taken. Now imagine your R1 value equal to R3. That means at the ALU stage, I come to know, and I am going to find out what is the target address, that is 36 at this point. But without knowing the first one is a branch, already some population has happened into the instruction pipeline. So these instructions which are already put into the instruction pipeline, this has to be fleshed out. So means they should not execute, or whatever action done by them, it has to be reverted back also. So now what you have to do is, there is an XOR instruction. This is what I need to fetch. So the effect of these three instructions has to be undone. We call it as flushing of the instruction pipeline. Now this will create unnecessary delay, or already some effort that is being done, the effort is wasted. Moreover, I have to make sure that whatever operation, so in the first operation already the adding happened and the output of ALU and some flag register can get impact. I have to revert back all these activities. I have to restore back. Now, how do you handle with this? Now, if you look into the conventional MIPS pipeline architecture, we know that out of the 5 states, let us consider as a branch instruction. So, whatever the branch instruction that it is been given here, that is branch if equal to, you have R1, R2, and I am going to jump into a location say 100. So this is R1 and R2 are going to be checked. So we know that the content of R1 and content of R2 would be read at this stage, and this pipeline register carries R1 value and R2 value, and ALU is going to subtract, and then I am going to see whether the output of ALU is going to be 0 or not. If it is 0, that means they are equal, and this will take a call regarding what is going. So you can tell that the normally PC plus 4 that is coming over here, and here it's a new target value, that is this PC plus 100. So out of this PC plus 4 or PC plus 100, one would be chosen, and that is based upon the output of ALU. This is the way how conventionally branches are being done. But looking at the impact, we don't know whether a branch will be taken or not taken until we reach this point. So there is an optimized way in which branches are handled. Can we rethink in such a way that can the branches be handled at the ID stage itself? For that, some kind of an optimization or some adjustments are required in the way how branch instructions are executed. Let us look into that. So this is known as an optimized MIPS pipeline, where the branching is addressed in the second stage of the pipeline. So how do you do that? So our conventional form of branch if equal to R1, R2 with some label, this is not possible in this case. I can only tell branch if equal to 0 or branch if not equal to 0, let's say R1. So what why we optimize in branches, rather than defining a branch instruction as comparison between two registers or R1 larger than R2 or R1 less than R2, nothing we can do. Now the branch is restricted to one register and see if that register value is equal to 0 or not. Okay, or that value is 0 or not 0. So what happens? I am going to read the value of a register that is from this stage, and I can check whether it is 0 or not. How do you check whether a register value equal to 0? Let's say this is a register with the 4 bits. I have to connect all of them into an OR gate, and if the output of the OR gate is equal to 0, that means all the bits are 0. So that is the way it is handled. So I need not go for an ALU stage in this branch. So I am redefining branches in such a way that branch is defined only on comparison of whether a given register value equal to 0. So anyway, I read the register value in the ID stage, then and there itself I can test for 0. So rather than comparison between two quantities, I redefine branches as test for 0. In that case, I could optimize my branch. Now, what is the advantage that I get? If I have one instruction, let's say it is already a branch instruction. So by the time in the decode stage, I will come to know at the end of decode stage whether a branch will be taken or not taken. If it is not taken, PC plus 4 is being used. If it is taken, whatever is a new address that is part of the branch. So this is there. I can do PC plus this XX, that is going to be my new target address. So in that case, I am only bringing one instruction. I have only fetched the instruction. And this instruction is normally the follow through instruction. That means if the branch is not taken. But at the end of the ID stage, if I come to know that a branch is taken, I need to flush out only this. So it has not done any decoding. So the penalty is only one cycle. So this is the way how are you going to optimize a branch. So this is a very important concept. If anyone has any query in this, how do you convert from a 4-stage or a branch which is handled in the 4th stage to a branch that is handled in the 2nd stage? Please let me know. So I am waiting if any student has any doubt with respect to how branches are handled in the 2nd stage. Is it clear or not?
Excuse me, sir.
Yes, yes.
Sir, why do we come to know that whether we have to take a branch or not at the 4th state? In the 3rd state itself, we can find that it's 0 or not
Okay.
in the
So,
execute state.
yeah. So the question that you are asking is in the conventional way, you will be able to know because the branches are defined with a wide variety of choices, less than, equal to, greater than, something like that. So in all these cases, I require an ALU operation, and ALU is a bulkier operation. By the time you complete ALU, after the ALU, there is one more testing that is required, right? You are able to understand that after the ALU generates a value, I need to check for 0. And then I use a multiplexer. If it is equal to 0, there is one possibility. If it is not equal to 0, there is other possibility. That means from where I am going to perform the next instruction fetch is dependent on the output of ALU equal to 0 or not, or larger than 0 or less than 0, whatever. Then in that case, I cannot complete this many operations. Apart from ALU completion, I need to perform a checking, and based upon the checking, a multiplexer has to give an output, either PC plus 4 or PC plus target. So that will be spreading into my 4th cycle.
Yes, sir. I got it, sir. Thank you, sir.
Okay. So anyone else, any other query? Because understanding this optimization from 4 cycle to 2 cycle is very much important, because we are going to learn about branch predictions today. Any other query anyone have? Feel free to ask and then clarify it. Only very few students attend the lecture. So those who come to the lecture, they should get the benefit. So this is a chance for you to clarify your queries. Okay. So in that case, let me go to the subsequent slides. Now, even we are trying to optimize from 4 stage to the 2nd stage. Still, I need to have a 1 cycle penalty. That means if the branch is really happening, then I have to eliminate that 1 cycle. Suppose if this is going to be a branch instruction, and then the second one, whatever I am bringing, that has to be flushed out. So there is a 1 cycle delay always there as when the branch is taken. When the branch is not taken, it is fine. Whatever you are bringing, without knowing the outcome of branch also, you will bring one instruction. That is generally the follow through instruction, and that will be taken. So basically in MIPS, there are 4 branch hazard alternatives. So first and simple approach is, the moment you fetch an instruction, you need to store, if you come to know it's a branch. So how do you do that? That's a bit tricky. So when you fetch an instruction, let's say I'm going to bring an instruction and the instruction looks like this. Okay, some ones and zeros. That's a 32-bit value. Now, once this is happening, if I have done my instruction encoding, I hope you have learned about different types of the instruction encoding. If I tell that if MSB equal to 1, that indicates a branch. If MSB is equal to 0, that indicates a non-branch. So the moment I saw the most significant bit as branch, during the fetching stage itself, I will come to know whether this instruction is a branch or not. If so, I should not fetch a next instruction. That means I am going to start the moment I come to know it's a branch. And how do I come to know without decoding an instruction? By intelligent encoding. When I do the encoding of instructions, probably the most significant bit or least significant bit or some predefined bit of the instruction has to be given like 1 or 0 such that branch can be easily identified. But I don't know what are operands of the branch, what is the target. The only information I get is whether the instruction is a branch or not. That's a more simple approach. And once you come to know the outcome of the branch, that is in the subsequent cycle, then you will know whether a branch is taken or not taken. Accordingly, you can fetch from the follow through instruction or from the target instruction. Now, the second concept is known as predict the branch as not taken. So here always we will assume that whenever a branch happens, we are going to predict that branch is not going to happen. So as usual, we are not bothered. I'll bring the subsequent instruction. And in the meantime, once I bring the subsequent instruction, I will come to know the outcome of the previous instruction. If it is not a branching, whatever you have fetched is correct. But if it is a branching, then obviously I have to flush that instruction. So I am ready to pay the penalty that is being required. The third option is known as predict branch as taken. So here I always predict branch as taken, but the problem is by the time I come to know the target address, it is the ID stage, so that will always have a one cycle delay. And the fourth option is known as a delayed branch option. Let us see one by one. So the first one is clear. The second one is predict branches are not taken. So what you do is you execute the successor instruction in the sequence, squash instructions in the pipeline if the branch is actually been taken. So let us consider an example here. So think of a case that you are having a branch instruction that is being fetched and assume it is not going to take. So by the time I am in the ID stage, I come to know, because I'm talking about optimized pipeline where the second stage is going to handle the branch. So at the end of ID stage, I come to know this is going to be not taken. So there is nothing to be done. Whatever I have brought, I plus 1, I plus 2, they are in sequence. So there is nothing that I am going to lose. So here I always predict branch as not taken, but there are two outcomes. Even though I predict branch as not taken, so not taken means going to the successor instruction. Taken means going to the target instruction. So if the branch is taken, but what happens? The moment I am going into the ID stage, something has to be fetched. So I will always fetch instruction I plus 1. Okay, that is fetched. But at the end of this, I am going, suppose the branch is taken already, but my prediction was not taken. So I need to flush out. That means this instruction will not go to ID, EX, mem and write back. And I'm going to fetch from the target. So whatever I have brought in this line, this is going to be now wasted now. I have to flush out the pipeline. So I incur a one cycle penalty. So one cycle, I am not going to fetch anything. Whatever I fetched at that time, it has to be flushed out. It has to be cancelled. So this is the penalty that you take. So this approach is very good when the probability that the branch not taken is very high. For those branch instruction with a very high probability that branch is not taken, predicting branch is not taken is the best approach. But if by chance, once in a while, if the branch is taken, that time you are going to incur a penalty. So what happens? Without knowing the outcome, I predicted, I brought something, and whatever I brought in was correct. Okay, so this is the way how it works. Now let us look into the third case, that predict branch is taken. But what happens? But branch target's address is not known by IF stage. So when you bring an instruction, I don't know what is the branch target. Because it is just ones and zeros. When will I come to know? I will come to know the target only at the outcome time. That means only at the ID stage, I am going to divide the instruction. Let us say this is my branch instruction. So I am going to define it as branch if not equal to 0, R1. Then I am going to define it as, let us say, 200. So the meaning is if R1 value not equal to 0, then I go to PC plus 200. So what I have to divide the instruction. I have to come to know it is branch if not equal to 0 on register R1 and 200. So I go and read the content of R1. I check whether it is equal to 0 or not. Only at that time I come to know what is the relative offset that I'm going to use. And then I have to add PC plus 0. So the target, which is nothing but PC plus this 20, 200, is known only at the time the branch outcome has come. By that time, already one instruction. So MIPS still incur a one cycle branch penalty. A prediction is always taken, but I have already fetched one instruction into the pipeline. Now the fourth one is known as a delayed branch. So here what you do is you define branch to take place after one instruction following the branch instruction. So in delay branch concept is we are redefining the operation of a branch instruction in such a way that the effect of the branch instruction will happen after one cycle following the branch instruction. So by the time you already have come to know the outcome of branch. So accordingly, I can determine. So one slot delay allows proper decision and branch targets addresses in a pipeline. So here MIPS basically use that. You have to find an instruction and fill it. So let me try to explain it. Let us say there is a branch instruction that is being given there. And the next one is known as a delay slot. And this is the instruction which you are going to run after you know the outcome of the branch. So it can be the follow through instruction or it can be the target instruction. So this one instruction, during the time I have to run, I have to find out another instruction which is must execute. So by the time I run the instruction, this instruction is not going to have any impact on this branch. So whether branch is taken or not taken, this instruction will be executed. But by the time this instruction is executed, already one cycle is over. So I will come to know. So this instruction is already in the ID stage. This will be fetched. So at the end of the ID stage, you come to know whether the branch is taken or not taken. And accordingly, I can fetch the target or the follow through instruction. So what I do is, this is my branch instruction. Now what I do is, this is known as branch delay instruction. So I am going to have branch delay instruction. So this if id mem write back, this will be surely executed. By this time, I come to know what is the outcome of the branch instruction. Let us say it is an untaken instruction. Branch is not taken. So the instruction I plus 2 that is going to be executed here. This is my follow through instruction. Now let us say the branch is taken. When will I come to know branch is taken? Only at the end of the ID stage. I am going to bring from the target. But that I am delaying by one cycle. So what will I do? I don't want to waste this cycle. There I find out a suitable instruction and then I am going to run in this case. Let us take some examples to understand. There are three possibilities by which I can find out a delay slot. So look at the branch. If R2 equal to 0, then I have to jump into this instruction. So this branch is defined in such a way that there exists one instruction immediately after this, which is known as a delay slot. Here you can see that the branch is done with the help of R2 equal to 0. I'm checking the condition of R2. So whether this instruction, wherein R2 is a source operand, whether this instruction is a must execute instruction, whether it is run before the branch or after the branch, if this is going to be compulsory, so delay slot will compulsorily execute. This portion is optional after that. Either it will be run from here or it will be running from the target mode. But this is always compulsory. So what I do is, I am going to replace whatever was there before the branch instruction. That instruction, this double add, R1, R2, R3, that I am going to put in the delay slot. So here I am filling the branch delay slot from an instruction from before the branch instruction. So this is the transformation that happens. Now sometimes you may not be always possible to find such a suitable instruction before the branch. So this is something from the target. Consider the case that you have always, there is a very high probability that the branch will be taken. So look at the branch. Here you have D1 R1 equal to 0, but this is dependent on this. So I cannot remove this instruction because this instruction is going to write into R1, and based upon that R1 comparison, I am going to this. So this is your target. Now you know that there is a very high probability that this branch will be taken. Under those circumstances, I'm sure that since a branch is taken, this instruction is going to execute. So I put this instruction. So in the normal time when it comes, this will be executed. And now onwards, the looping is happening here. So I put this instruction here. For all subsequent times, I am going to redirect it to one instruction after this, such that this will be running in the delay slot and will be compulsorily executed. But what happens if my branch is not taken after some time? Let's say this condition is not going to happen. At that time, whatever I'm running, I am only fetch this. I have to flush it out whenever a branch is not taken. Now, the other approach is, this is branch taking from the target portion. The other one is taking from the follow through portion, just reverse. So here, my branch is dependent on R1. So I cannot relocate this because I'm going to write into R1, and based upon that, my branching is going to take place. And what happens? This is the instruction that I will run if the branch is not taken. So I will put that OR instruction in the delay slot. And this is something that is your target instruction that will run as such. This is highly suitable when there is a probability that the branch is not going to happen. So this is the very much, this is the heart of the branch delay slot. If anyone has any query in this, please let me know.
Sir, I have a query in the where we are predicting the branch will happen or not.
Okay. You ask me. Your doubt is not
Sir,
clear.
how do we know before that when we're predicting? How do we know that the chance of get the branch being happening? We like the percentage should be or more than 50%. Then we should say yes. We will predict
Yes.
that yes, branch will happen. So how we know before?
So see, essentially in architecture, it is some set of instruction that is going to be stored in memory. And how do you get the instruction? Compiler is going to help. Compiler is generating this instruction. So suppose if I have a for loop for I equal to 0, I less than 10,000, majority of the time the loop of the I is going to execute. So compiler will give a indication to the hardware that this is that out of 10,000 times, close to 9,000 times this branch is going to execute. So the hardware will come to know whether such a kind of branch prediction will happen or not. So what the compiler does is, at the time of generation of the code, since compiler know the architecture is using a branch delay slot mechanism, and compiler knows the meaning of the loop and what is the probability. This is possible only for a for loop. But some branches it may not be possible. In that case, I will free the branch delay slot as such. So filling up branch delay slot is not always possible. Wherever possible, if you can find an instruction which is must execute, then only I can fill it. And that happens from past analysis. What happened to this particular instruction when it was executed previously? Can it reordering be possible? We will learn about that in subsequent slide. But anyway, it's a statistical computation.
Yes, sir. And sir, in delay slot, we put whatever instruction. How we ensure that that instruction is going to surely run it? How we ensure that?
Even if that instruction, see, my idea is that cycle should not be wasted. I have to fetch some instruction and carry out the execution. So there is an earnest effort that is put in to find out such a suitable instruction. In the first category, whatever you're seeing, the extreme leftmost, that is a must execute instruction. Sure, right? Whether the branch is happening or not, this is an instruction before the branch. So I can pull up in the delay slot. The hardware is configured in such a way that whatever is in the delay slot, that instruction should be executed. That is the way how the control logic is designed. Now, the second and third case, there is only a gut feeling. Those filling up of delay slot like that, like from the target or from the follow through, is recommended when there is heavy probability that branch is taken. So if the branch is going to be taken, then find out an instruction from branch target. If the probability is very less, then find out from the follow through. I will fill it. Now, what if actually the branch is not going the way how I thought? Only problem is I will fetch an instruction. I have not decoded. So I can always flush it out. But in majority of the cases, my delay slot is giving me performance 1 in 1000 or 1 in 100. So for example, there is a for loop of 100 times. 99 times whatever I put in delay slot is correct. The 100th time whatever I'm putting, that may be flushed out. So there is always a checking, double checking whether whatever is put in delay slot is really needed or not, which will come to know after the program on.
So what is the benefit of putting some instruction in delay slot?
Now, what happens if I am not sure about what is the outcome of the branch? As long as branch is not taken, if I'm not using any other brain, still whatever I bring from the follow through instruction, it will be executed. But what if the branch is going to be taken? If the branch is going to be taken, normally what will I bring? I bring the follow through instruction. It has to be flushed out because the branch is going to be taken, which I will come to know only one cycle later. Rather than follow through instruction, why can't I find a must execute instruction independent of the branch outcome? That is what we are trying to do. I am trying to improvise on predict taken scenario. Did I answer you correctly, or if you rephrase your doubt, I may be able to explain once again.
Yes, sir, I got it now. Thanks.
Okay, okay. Anything? Any other doubt? Anyone?
Sir, in the B part from the target itself.
Yeah.
Yes, sir, if the double subtract operation depends on the R1, then we can't put in the delay slot, right?
In the second portion, if the D
Double
sub is
subtract
dependent on, if that is
R1.
dependent on R1, no. It has, you have to find an instruction that is independent of the branch instruction or something like that. That is the reason that it is not always possible to find an instruction, but your compiler sometimes will search up and down and then find out a suitable one such that I need not want to waste one cycle slot. I wanted to fetch an instruction always in every cycle.
Okay, sir.
Any other query, anyone? Okay, let me go to the subsequent one. Now let us try to understand, rather than statically predicting whether the branch is happening or not happening, can I predict it dynamically, runtime, based upon some learning, some machine learning I'm going to teach you today. When do you know you have a branch? You will come to know whether a branch has happened only at the ID stage, because that is the time when I am decoding the instruction. So certain bits in the instruction will tell me, okay, this is a branch instruction. So when do you know whether a branch instruction is taken or not taken? That also happens at the ID stage, because at the ID stage is what I'm using. Suppose if I am not optimizing my branch, then at the end of EX or at the MEM stage only, I will come to know of my previous branch instruction, wherein only at the fourth stage I can come to know whenever the branch instruction is comparison of two registers, larger than one, larger than other. But test for zero only can be done in ID stage. So you will come to know whether a branch is there only at ID stage, and whether a branch is taken or not taken, that also at the ID stage. But modern pipeline that is being used in the Snapdragon processor, that is being used, Qualcomm Snapdragon processor, then Core i3, i5 processors, rather than 5 stages, they are all having more than 10 stages. So instruction fetch and decode itself will be 3 or 4 cycles. So modern pipelines are very deep pipelines, but several instructions are issued per cycle. We will learn about it. Now we are learning only fetching of one instruction per cycle, but subsequently we are going to learn about more than one instruction. So several predicted branches will be there already. So these all things will make things complicated. So we need to understand how to handle with the branches. So let me introduce you to the concept of dynamic branch prediction. So execution of a branch requires a knowledge of what is a branch instruction. That is, encode whether instruction is a branch or not, decide on taken or not taken. So now the question is, can I predict whether a branch will be taken at the IF stage? Then only I can save the penalty. So that means I am bringing an instruction. At the time, I should be able to know this is a branch instruction. And then if it is a branch instruction, I should be able to predict whether this branch will be taken or not without looking at the operand. My actual outcome, I will come to know in the very next cycle, if it is a 5-stage pipeline, can I predict whether something is branch or not in IF stage itself? And then and there itself, I predict whether it is taken or not taken, such that none of the cycles I am wasting. The branch will continue, but what I am bringing next, the next instruction fetch, I can accordingly plan. So whether a branch is taken or not taken, I have to find out with the help of a prediction mechanism. If the branch is taken, what is the target address? So if the prediction is going to be telling that this branch is going to take, then I should know what is the target address, because I have to compute PC plus target address. So where will I do that? I have to add it, no, current value of PC plus target address. So this I can do only after knowing what is outcome. So can it be computed? Can it also be pre-computed and stored somewhere? That is what we are going to explore. If the branch is taken, what is the instruction at the branch target address? Can you save that? Let's say there is a branch instruction, there is a jump instruction here, it's 2000. Now in 2000, there is another instruction called add. So let's say this is a 1000th instruction. So by the time I fetch instruction from memory location 1000, can I know whether it is a jump? I don't know the operands. I'm still working on it. So 1000 is a branch instruction whose target is 2000. So if the prediction is taken, I can immediately go to 2000 also. By the time I decode it, I have already fetched the instruction from 2000. And if the actual outcome is going to be taken, so whatever I have brought is correct. If actual outcome is not taken, then whatever I have brought this, I have to flush out. I have to bring the next instruction. So what we use is we use a concept called dynamic branch prediction, where there is a small hardware unit that is connected to the instruction fetch. It is known as branch prediction buffer. It's also known as a branch prediction table or a branch history table. So dynamic branch prediction, it uses a branch prediction buffer, and the branch history, the same name is there. So what it stores, it records the previous outcomes of the branch instruction. And then we have to index into it based upon the previous outcomes. So branch history table is nothing but it records the previous outcomes of the branch instruction. Now, a prediction using branch prediction buffer is attempted when the branch instruction is fetched. So as and when I fetch an instruction, in the fetching stage itself, there should be some mechanism by which I come to know it is a branch. Then I refer to this branch prediction buffer to some entry. I will find out what is the mechanism, which row I will refer to. And that entry is going to tell you, okay, this branch will be taken. If it is taken, this is the target address. Then I go to 2000 and bring. Let's say I am indexing into this entry and I is telling it is going to be not taken. Not taken means there is no target. Whatever is the current PC equal to PC plus 4 that I can run. So it's acted upon during the ID stage. So when you really come to know what is the outcome of the branch instruction, we can make appropriate modification in the branch prediction buffer such that a revisit to it in the subsequent time, I can take a better decisions. So branch prediction buffers are something similar to what we refer to kind of an astrologer. You go and tell that, let's say there is a marriage alliance between two persons. You go and consult the astrologer and ask, is it okay if these two people are going to marry? Then astrologer will look into many other parameters, statistical parameters, scientific parameters, and then tell, okay, this is good, this is bad. Like that, you are going to ask, like, whether today it will rain. You are going to consult someone and they are telling, okay, there is a heavy probability of rain. So someone from an expert from meteorological department, they look into many things. So before the actual outcome of an event, I am trying to predict. So branch prediction is very much close to what is there in the real time. Similar to the, let's say we see an astrologer and astrologer telling everything is fine. Later, if actually you come to know that the real life story is totally different, these two couples cannot get along together, and then you tell the wordings of the astrologer, the prediction of astrologer has also, let's say the prediction happened to be wrong. Third time, you are more aware. Okay, last 2 times I consulted the astrologer, but the outcome was not in correct with the prediction. So your confidence level in the astrologer will dip. When someone else asks you, how is this astrologer? This is what you are going to tell. Okay, so that is the way how you learn things over time. So in dynamic branch prediction, we have have to use two things. Are you going to make a prediction or not? Sometimes I cannot make any prediction. I can simply leave it. So whether prediction is made, if the prediction is not made, then bring the follow through instruction. Now the second aspect is, based on prediction, you bring the next instruction, but you may have to see later at the end of the ID stage whether the prediction was correct or incorrect. There are two possibilities. Case one, yes, I am making a prediction and the prediction was correct, or the default was correct. In this case, there is no delay at all. So case one is, there are two questions that is been asked. First one, are you going to make a prediction? It's an yes or no. Second one, the prediction was correct or not. So case one tell that, yes, I made a prediction and the prediction was correct. That means whatever I brought in, that is correct. Or I didn't make a prediction, but whatever was the default, that means the follow through was correct. In those cases, there is no delay at all. In case two, I made a prediction and the prediction was incorrect. My prediction was taken, but actually it was not taken, or vice versa. My prediction was not taken, but actually it was taken. This is one case. Or no, I didn't use a predictor, but the default was incorrect. In these cases, there is going to be a delay. This is what we have to understand. Now, prediction scheme, sometimes I use finite state automata. You might have learned in some other subject before what is going to be this finite states. So let me take a 1-bit predictor system where there are two states for it. When you are in state 0, then you tell that the prediction is not taken. Similarly, when you are in 1, the prediction is always taken. Now there is a transition. So when you are in 0, then predict branch is not going to happen. That is what is my prediction. When you are in 1, then predict branch is taken. Now imagine, let's say there is a minor mistake here. Let me correct it. So the state is being defined like this. So 0 means not taken, 1 means taken. Now let us say when you are in 0, the actual outcome was taken. That means I move from 0 to 1 through this edge. My state is 1. So next time when the same entry is referred, I predict as 1. Let's say you're already in 1 and it is taken. So I will continue in this. When the actual outcome is not taken, when you are in state 1, actual outcome is not taken, then you move from 1 to 0. And if the actual outcome is not taken, then it goes like this. So this is a 1-bit automata. So as long as you are in state 0, you predict as not taken, and the actual outcome reinforces your prediction, then you continue in state 0. Similarly, when you are in state 1, actual outcome is taken, prediction is also taken, then you continue in state 1. When you are in 0, and if the actual outcome is taken, then you shift the state, and vice versa, from 1 back to 0. Similarly, I can use a 2-bit automata also. The use of a 2-bit predictor will allow branches that favor taken or not taken to be predicted less often than the 1-bit case. This is known as a reinforcement learning approach. So I am starting with 0, 0. So these two, the bottom two states, as long as I am in the bottom two states, my prediction is not taken. When my current state is the top 2, 1, then my prediction is taken. That's why it's written as predict taken, predict taken. These two are predict not taken. In 0, 0, if it is not taken, continue there. In 0, 0, if it is taken, I move here. From 0, 1, if it is not taken, I come here. From 0, 1, if it is taken, I go up. So if there are two missed predictions, I am going to move from 1, 1 to 0, 0, and from 0, 0 to 1, 1. Remember, there is no arrow from 0, 1 to 1, 0. That's the way how it is being defined. So branch prediction in hardware, how do you do that? Branch prediction is extremely useful in loops. A simple branch prediction can be implemented using a small amount of memory. That is what is known as your branch prediction buffer, indexed by the lower order bits of the address of the branch instruction. So how do I go into this? With the help of the address bits, I am going to refer into this. 1 bit stores whether the branch was taken or not. So this particular table will have one entry which will tell 1 or 0, which will tell this branch is taken or not. So next time, so what happens is I have a branch prediction buffer. Let's say now there is a program whose PC value is this. Using the least significant bit of PC, I enter into this. And there may be different combinations. And this will tell you with 1 or 0. 1 means this particular PC indexed into this branch prediction buffer, that is there. That means the branch is taken. Otherwise, the branch is not taken. If the branch is taken, then there is a target address which will be telling that go to location 2000. So I am fetching. Before decoding itself, I come to know next instruction is to be fetched from 2000. So I go and fetch from 2000. By the time the fetch from 2000 is over, the decode of the previous branch is done. So the outcome is known. So I am confident that should I continue with this 2000 or should I flush out 2000. There are a basic 2-bit predictor for each branch. There is a predict taken or not taken. If the prediction is wrong for 2 consecutive times, change the prediction. That's what we have seen, a 2-bit predictor. So sometimes you may have correlating predictor. That means multiple 2-bit predictors are there for each of the branch. One for each possible combination of the outcome of the preceding n branch. So what do you do in the case of a correlating predictor? What I am doing is I am looking at the outcome. The outcome of a branch is dependent on preceding n branches. So consider this case. If x equal to 2, then x equal to 0. If y equal to 2, y equal to 0. If x not equal to y, then only do this. So your branch 1, branch 2, and branch 3, there is a dependency between them. If first branch and second branch happen, then third branch will not happen. So the outcome of this is not dependent on the previous iteration of the same branch. Outcome of this is dependent on the previous n branches. That is why correlating predictors are used like that. The local predictor is you are using the last n occurrences of this branch. So the same branch, let's say there is a go-to statement. Its go-to statement is inside a for loop. So every time you go to this particular instruction, you look into what happened to the last time this particular instruction was executed. So last n iterations of the same instruction, whether they were taken or not taken, based upon that, I make a call. What should I be doing with this cycle? Similarly, you have tournament predictor. Tournament predictor is nothing but you combine correlating predictor with the local predictor. So many prediction circuits are there. I request you to refer to the textbook to get a clear understanding of this tournament predictor. To reduce branch penalty, know whether the ask yet undecode instruction is a branch. If so, what is the next? So what we do is we have learned about branch prediction buffer or branch history buffer. The other one is known as branch target buffer. So here what we do, if the instruction is a branch and we know what the next PC should be, then we can have a branch penalty of 0. So if you know that it's a branch instruction prediction is taken and what is going to be the next PC, then I can directly fetch from that instruction. A branch predictor cache that stores the predicted address for next instruction after a branch is called, then we call it as a branch target buffer. This is been facilitated by a branch target buffer. So what will branch target buffer holds? Branch target buffer holds the current PC plus the next PC. So I'm telling if I bring something from 2000, it's a branch and it is going to jump into 4000. So I'm putting the next PC also. So I can directly go. So the computation of the next PC, that computation is over. Already the next PC value is kept a priori. So this is how it looks like. The branch target buffer looks like. Some entries are there. And the PC I'm going for lookup. Whenever I'm going to give an instruction, I see whether, suppose I'm going to bring from 2000. I see whether 2000 is present there. Okay, let's say there is 2000 present here. And that will tell that 3500 is the predicted PC. So I go into this location. So the current PC value, the set of all possible branches, its program counter value, and their program counter value of the target address, that is being saved here. And this will tell you whether the possibility was taken or not taken. So if taken, then this is the target address. If not taken, go for this value plus 4. That's how it is being done. So this is how all general structure of branch target buffer looks like. The current PC value. So there is a jump from 3340 into 4460. So 3340, I enter into the table and 4460 is there and I'm predicting it as taken. Similarly, from 4520, I am jumping to 3320, the prediction is not taken. Sometimes I can put prediction as not taken also. That means the last time it was not taken. Then I will put accordingly. Now, branch history table. So I can refer into this with the help of last n bits. What happened? Last branch not happened. 0 indicates branch not taken. So the last 4 occurrences of the branch sometimes also is used to index into the table. There are different ways in which I can keep the history table. One is an exclusive entry of the PC. Second one, last few bits of the PC. Third one, outcome of the last n occurrences of the PC. That's the way how it is being done. So branch folding is a special mechanism. So what you do is, rather than storing the target PC, you store the content of 4. Let's say the 4460 is going to store an add instruction. So the moment you store an add instruction, then that is what is known as branch folding. So optimization on branch target buffer to make 0 cycle branch. So you make the branch target buffer little more larger. What you do, rather than storing the next PC, I store the instructions. So I fetch the current instruction. In between, I refer into the table, and table will give me what is a target PC and what if would have brought the instruction that I'm going to fetch. So this IF is for the first instruction and IDEX all are for the second instruction. What is second instruction? It is a target of the first instruction. So I fetch the current branch instruction. From the table, I get the target instruction, and the target instruction I'm going to put up into IF EX pipeline register, and then I'm going to look forward. So add target instruction into branch target buffer to deal with longer decoding time required by the larger buffer. Cycle conditional branches. So this is the section that I have used for referencing to this topic, major hurdles in pipeline, especially go to branch results and how is pipeline implemented. So there are a lot many pages that are being covered from the textbook every day. You request to go through. At the same time, you can refer to this NPTEL video also as the reference. So let me see whether there are any queries. And one more thing, on Monday we have a problem solving session. So some numerical problems, I will share it with you tomorrow or today itself. Try to work it out, and then Monday we will solve it in our online session, how to approach this. And the problem solving session, the slides won't be shared. So whoever comes, they only will be able to know that, because I am going to manually solve it. There is no slides prepared. Any queries?
Sir, when we run some algorithmic programs or some other programs, we depend on the hardware to solve those algorithmic functions or something like. But when we are building the hardware, we themselves we are using these machine reinforcement learning and other things. But we depend on hardware for solving this. But here we are using these much algorithmic or some machine learning approach to build hardware only.
So here we are not completely using an algorithm. We have smaller circuits whose basic functionalities, like you refer, you collect statistics, and then you store. So some tables are there, the tables are populated, you look into the table. So these are all algorithms implemented in hardware. So it's not like fetching and all. The control logic in such a way that it will look up, it will search. So you can have a searching circuit completely in hardware with logic gates. They will look in each and every circuit, and then this is the way how you do. So even though all your programs are going to run on hardware, in hardware itself, we have extended circuits which will perform the basic hardware operation at much nanoseconds level speed. So hardware is designed like that. So you have learned about basic control logics, and using the basic control logic and logic gates, we can implement such kind of small circuits which can perform searching, lookup, multiplication, adding, and all. They are all not as complex as the bigger algorithms that you have learned or you are learning in this semester?
Yes, sir.
So on March 6th, Saturday, there will be the second quiz. You will get the mark of the first quiz today or tomorrow, and you will get a mail, just like the way how you got question paper. So that for that, whatever is the rest topics covered after the first quiz, and whatever the topics I am teaching now, both of them will be there. So try to prepare, and then April 15th onwards, you have Viva. So during the Viva session, simply looking at textbook also may not help. Some of the points and things discussed in the online sessions may also be asked. It's a one-to-one Viva, so you don't get much time to discuss or look here and there. So try to tell your friends to come to the class and attend, or else at the end it's very difficult to make it up. I'm seeing that the number of students are very limited. Of course, 30 students who are very regular, they are coming. But in a class of 192, if students are not going to attend, seriously, you will miss the marks. And if you miss the mark in COA, the next semester operating systems and OS lab also is going to be extremely difficult if you don't know the concepts. So tell your friends who are not attending to come and attend if you find attending classes are useful. Any other query? So if there is no other query, students can leave. But if someone has any query, I will stay back for 5 more minutes, if at all anyone has any query.